close the door.
All right, thanks everyone for coming. So it's a great pleasure to introduce Lauren Zamora. She is now an associate research scientist at University of Maryland, joint with NASA Goddard Space Center. But I guess what makes this such a privilege is that Lauren was a student here, graduated in 2010, and has been wanting to come back here for a while and meet up with people at Rosenstiel, and it's great to finally have this opportunity. And Lauren has had an amazing career, and it'll be wonderful to hear about it. So, and I just heard a story that Lauren brought all these samples back that she had collected during her PhD. So mind you, she graduated in 2010, and to incorporate into Cassie Gaston's lab. So that's amazing that Lauren has dragged those around all these years, but that gives you a sense of the high caliber of our alumni. So,
thank you.
Can I have the microphone back?
Yeah, we'll bring it over.
Great. Well, this is really an honor. I'm so excited to be here. Like Paquita said, I mean, this is like so exciting for me to come back after all these years and get the opportunity to talk to you guys and kind of reflect on like what things have been like since I've been an alumna, or since I graduated. So anyways, thank you so much for inviting me. I'm really happy to be here. And so I'll get started. So just a little bit about what this seminar is going to be about and what it's not going to be about. I was asked to do kind of a career retrospective, so I'm not going to get into great detail about the knowledge of the general field. This is mostly going to be about stuff that's related to my own work and sort of the lessons that I've learned kind of going through it that I hope maybe can be useful to some of the students. Okay, so just to get started, I wanted to talk about some of the science that set the stage for about a decade of my work. So I was a student of Dennis Hansell's here, and Dennis Hansell got a grant with Frank Malero and Joe Prospero to study the excess nitrogen in the subtropical North Atlantic, and so that means nitrogen that's in excess of the Redfield ratio, which is 16 nitrogen to 1 phosphorus. And he had this paper, this is the subtropical gyre here, showing that we have this high levels of nitrogen, of what they call N-star, due to not just nitrogen fixation, but also anthropogenic and just in general atmospheric nutrient deposition. So that he thought in this paper it could add an extra like 38% of the nitrogen, this excess nitrogen. And then at the same time, Joe was here. He has this really long time series station. Now Cassie's taking it over. Too many publications to list, but he was a giant in the field of aerosol science. He had this long-term site at both here in Miami and at Ragged Point, and Lillian's contributed to that over many years. In fact, this is Lillian here walking towards the container there where we work. So those two papers were kind of set the stage for me working here. And then the third kind of really big paper was this paper by Deuce et al. In 2008. So I was a student here, and Dennis was kind enough to let me go to a workshop that had nothing to do with my own work on I think it was agriculture. And then Rasmus had these student fellowships that allowed students to go to random things they wanted to go to, and so I did. And when I was there, I met somebody who invited me to this other workshop, which ended up being really, really impactful for my career. So it kind of shows how your career can, random connections matter. So at this workshop, it was a workshop on how nitrogen affects the ocean, and Joe Prospero was also there, and we came together and just did a bunch of back of the envelope calculations. We found nitrogen supply is increasing rapidly. And in fact, this is how much they think it would have increased to 2030, which is almost now, basically. So it's kind of funny. I don't know if it has actually increased that much. It'd be interesting to go back and see. But at the time, this is what we were thinking. They were going to have large amounts of nitrogen being added that weren't there before. And this would draw down some CO2, and potentially some of those effects would be offset by nitrous oxide emissions. But this is all back of the envelope calculations. There was a lot of remaining questions, like how much deposition would be added, what were the actual effects on CO2 and nitrous oxide and so forth. So this kind of motivated a lot of my work, and in fact, other people's work too. It's already been cited over 1,000 times or something. So the first question, and this was part of Dennis and Joe's grant, was to understand how much excess nitrogen gets deposited to the ocean if you include the organic fraction So similar to what I think still gets done today, we collected rain, we collected bulk aerosols, and indeed we found that the ratios were still well in excess of the Redfield ratio. There hadn't been much information known yet about soluble phosphorus, so we found that it was about a third or so of the total amount. And in the first kind of bit of information showing maybe we had overestimated things with Thus, we found that like less than half of the organic nitrogen that they had back of the envelope calculated for the paper was actually observed, at least in our samples. And then last, we found that a lot of the organic nitrogen was actually in the form of some kind of volatile basic organic nitrogen, and this was actually one of the first papers showing that maybe something like urea or amines could be important. And so it wasn't really what we're focusing on, but that's what ends up what this paper actually got mostly cited for. And now, of course, Cassie's done a lot of extra work, and Barkley, Joe Prospero, lots of other people have done extra work, and so this isn't meant to be kind of the final story. This is just something we did at that time, and then there's a whole bulk of extra research that's been done going on this kind of direction since then. So then at that same workshop, I met this guy called Andreas Oschlies. He's a German scientist, and I decided I wanted to kind of try out biogeochemical modeling, and so I got invited to go out there. And it was nice. They actually paid me a little bit extra money, so I made money, and they paid a place to stay and everything. And so we did this paper together on biogeochemical modeling of the ocean. And our question was like, what happens? So now you're adding all this excess nitrogen, but what happens to it then in the ocean? And we couldn't really answer that fully, but we found some of the important uncertainties. Which is at least part of the problem. So here's a map of the deposition of nutrients, and you can see that most of it's deposited here near the Gulf Stream. So if you deposit nutrients in the subtropical gyre, they'll sink and stay in the gyre. But if they get deposited near the Gulf Stream, that water is moving fast, and so assuming nothing happens to those nutrients, they actually stay near the surface and then get subducted and go back into the gyre. But if the export happens quickly or at an intermediate step, then you have, like for example, if phosphorus is preferentially remineralized or if excess nitrogen is taken up, then it turns out that it sinks faster, and then it goes to deeper waters that then don't come back into the subtropical gyre. So where it's deposited and what biology happens is important to its long-term biogeochemical fate. And I just want to mention this is more for the supervisors of students, but I found these experiences really valuable. Fieldwork, getting a chance to study abroad for a little while, and participating in workshops, even if they don't seem related, those things ended up being super valuable for my career. So, you might consider that for your own students. And for the students themselves, some of the lessons that I learned as a student here that might be helpful for you. Well, first off, let me quick talk about this figure. I don't remember who took this during ARCSIX, but I really like it because it kind of reminds me of science. You're walking on a path, you don't actually know where you're going per se. You have an idea where you want to go, but you don't know exactly where you're going to end up. And you're walking with people. Like there's people who are helping you, people who you might be helping, people who you might have competitions with, but you're all on this journey together. And that's a really important thing to keep in mind as you go through your career. Like the people around you are super important, and they're going to make you better. Some of the things that I learned, so good communication with your advisor and your committee is really helpful. I know I needed a lot of tough love. Lillian can say, there's a lot of lessons to be learned when you're a student, and sometimes you need that tough love, but you also need consistent support, and that I got that, and both of those things are really needed for me to be successful, and so I was lucky to have both. It's helpful to have a range of mentors. So for example, your PhD advisor is a super important mentor for you, but no one person can be everything for you. So it's helpful to have conversations with other faculty members, with people outside your institute, with fellow students, even your personal friends. Like you need all of those people in your life to kind of help support you, because it's hard. Like being a student is hard. Anyways, so these personal connections really matter, and also just have faith in yourself. It's pretty common that you feel like you're failing. I've talked to many students; they all feel that way. I felt like I needed a lot of help, I think, and it's okay to make mistakes. That's really actually important, just knowing that it's going to be okay. Just get if you fall down on this road here, you just got to get back up. You're going to get somewhere interesting and somewhere good, and it's okay. So after I graduated, I got recruited by Andreas again to go work with him in Germany, and this ended up being the only place where both my husband and I both got jobs, so it was luckily we both got something. He's a scientist too. And we continued some of the work from this Deuce paper. The question now was, does this atmospheric nitrogen deposition still lead to meaningfully more amounts of nitrous oxide emissions? So nitrous oxide is a greenhouse gas. The emissions from the ocean contribute to 10 to like 30% or so of the tropospheric levels. Most is emitted in tropical regions. Like here's a plot from the Eastern Tropical Pacific, for example. Mostly in areas with low oxygen, but at super low oxygen anoxic levels, then nitrous oxide actually gets consumed. So in our hypothesis in the Deuce paper, we just said assume linear, like every amount of nitrogen you add in, it's going to result in nitrous oxide emissions. And you can see maybe that's not the best assumption, but it was a starting point to kind of jumpstart the science. So fun fact, Science Magazine actually got sued because of that. Like some geoengineering company that wanted to do ocean fertilization didn't like us publishing that. That's not the best way to go about it. If you don't like somebody's science, that's better to actually do the science to kind of prove them wrong, which is what we ended up working towards ourselves. So as a postdoc, I had to develop the nitrous oxide model. So I used a bunch of data from this Memento data set. And I calculated various parameters for the model. Like, for example, we needed to know how quickly it gets consumed in anoxic areas. So we looked at this Peru-Chile undercurrent, and it's this like pretty, not much flow leaves that current. It's a quick current that goes like from about here to here. And so you can see like N star decreases, nitrate increases, nitrous oxide decreases. So this is all showing that you have nitrous oxide consumption from denitrification in this water. So we could calculate approximately when the water entered and when it left, and then get information on some of the consumption rates in situ. We calculated from this new data set, at what oxygen level you get nitrate, and that tells you something again about where it gets, this consumption begins. So I did this kind of parameterization first, and then somebody beat us to the quick, though. My colleague Parv she found in her paper that atmospheric nitrogen deposition does not meaningfully contribute to more marine nitrous oxide emissions. But we went ahead and did the study ourselves with our own model. Sorry, this is kind of hard to understand. These are different like uncertainties in how much nitrous oxide emissions get emitted in our model. And down here, AD, that's atmospheric deposition, and it's relative to this bar here. So you can see it's basically negligible. There's like hardly any impact of atmospheric nitrogen deposition on the nitrous oxide, at least in our model. But it ended up that we found this whole new uncertainty, which is the amount of nitrification-derived N2O at the surface. And that ended up being a really big uncertainty, partially because if it happens, it immediately gets emitted to the atmosphere, and you don't know, you can't quantify it. You can't tell nitrous oxide from space very easily, unlike some other gases. So it's a pretty big uncertainty. And then later, some colleagues, we continued using this model and looking into some of the Deuce questions, basically. And so Landolfi, this is a colleague of mine, found that this larger atmospheric nitrogen load is offset by, if you have a lot of nitrogen being added in from deposition, then you just have less nitrogen fixation that happens. And so it kind of balances out, which is something we hadn't considered in the Deuce paper. Sunflower-Lingham found that actually an exception might be the North Indian Ocean, because there you're right on that border of anoxic and suboxic, where you have really high amounts of N2O and very low, where it gets consumed. It spikes from really high and then it immediately gets consumed. And so small amounts of oxygen changes in that basin could matter, but no one, to my knowledge, has actually really looked into that since then. And then finally, we revisited Deuce et al. 9 years later in Jickles et al. And found that, at least with the updated models at that time, that we had sort of overestimated CO2 uptake by about half or so. And I bet that the field has moved on since then. I'm not up to date on this field anymore. Cassie, you could probably tell me more about what the current state is. But those are some of the papers that kind of I was part of, that kind of derived all from that one Deuce paper. So I wanted to talk a little bit about science abroad, as I got to do in my PhD and then as a postdoc abroad, and some of you might be considering that. There are a lot of pros. I totally recommend it. You get to travel, this is important, you get to learn different ways of doing science. So, for example, in Germany, they have much larger groups than in the US. You have research scientists, which is like a lot less common here. And that's how I got the idea for myself that this might be something I'd want to do, because there you have many fewer professor positions, but people just stay and do research in those groups. They have like groups of 30 people, and that's their career. And that sounded really interesting and attractive to me. So they have longer grant periods, like 9-year grant periods. That's amazing. You can actually do science instead of write grants your whole life. Shorter PhD times, I think there's like 3 years instead of about 5 here. They have different views on work-life balance. And importantly for me, I had children when I was there, and they give you some support for starting your family. So they have like paid parental leave, partially paid childcare costs. My children even became dual citizens in Germany. So these are all nice things that, you know, there are cons. There's culture and language barriers. There's more paperwork, more taxes. I found it's harder to stay relevant here than, you know, in the US if you want to come back. Some of the students here might be international, and they might have different thoughts, that, you know, on their own. That would be interesting to hear from them too. But so, and then there's like exchange rates that could be good or bad. If you come back, suddenly you have made a lot less money or a lot more money, depending on what the exchange rates do. It hurt us when we came back, because suddenly the money we had saved was like worth like 70% of what we thought it had been. Anyways, these are things to consider as you if you're considering studying abroad. And then as some lessons learned from being a postdoc. So the two-body problem is real. That's something it's hard to deal with. I think Erasmus is really good because they are very encouraging of couples, and I think that's really helpful, but many places aren't. So I think you got to be flexible, be willing to like maybe not take your perfect job, apply many places and just see what happens. Don't be afraid to ask for opportunities either. If you don't see any that exist, you can contact people. It can be easy to burn out, I found, and so it's helpful to have like family and friends that can support you. So, okay, so then I moved back to the U.S. I wanted to come back to the U.S. My parents are in the U.S. I wanted them to be near my kids, and I was looking for oceanographic jobs. There weren't any, so I wanted to do something atmosphere related. NASA Goddard Space Flight Center happens to be in DC, and one thing they're interested in is aerosol-cloud interactions. And so I was looking into that, and this is a figure from the IPCC report, and here's the uncertainty from nitrous oxide, and keep in mind, marine nitrous oxide is only like a third of that. And here was the uncertainty from aerosol-cloud interactions, so I thought, you know, this might be something really worth doing, and you know, if I have to change fields anyways, this was what I want to do. So I started focusing on aerosol-cloud interactions in the Arctic. And so for those of you that don't have a background in the Arctic, it's a really quickly changing system. It's warming 4 times faster than other places. It impacts like not just the Arctic, but other places too. It impacts sea level rise, weather, planetary albedo feedbacks, permafrost thawing, ecosystems. So it's a really, really important system. And you have a lot of these low-level liquid-containing clouds, kind of similar to this picture there, that are prevalent, and their radiative impacts aren't really well known. They're hard to observe from space, for example, if they're over the sea ice, and it's dark part of the year, and it's harsh to sample at the ground. So it's a pretty unknown system, even though it's an important system. And we know, you know, we're not sure how it's going to change as it continues to warm. With some other background about the Arctic, it's often really clean in the summer, and so clouds can be particularly sensitive to aerosols. And there's a lot of, like I mentioned, challenges in observing there. Bright surfaces, lots of clouds, so that makes it hard to observe aerosols from space. You don't have, this is a problem globally, but you don't have a good way to observe cloud active particles like cloud condensation nuclei or ice nucleating particles in many places. And a lot of the microphysical processes aren't very well known, so the models have a lot of uncertainties too. And then plus, since the Arctic is changing so quickly, that also makes it pretty uncertain. We have all these aerosol sources that are changing. You have leads that are opening up, emitting marine aerosols. You have more shipping. You have increasing amounts of fire in the boreal regions. You've got newly exposed land like here, and then that leads to more dust emissions. You have all these micro nanoplastics. This is a picture from where we were near in Greenland. Not from us, but from a previous study there. And look at all those microplastics in the ice. It's totally disgusting. And then you have all these feedbacks that are occurring at the same time. And then as it's warming, that affects, for example, ice nucleating particle activity. If it's warmer, ice nucleating particles need to be more effective to freeze at the same temperature. And then we have changing emissions of moisture and heat, and that affects clouds. And then now more recently, people are starting to talk about climate intervention. For example, polar mixed phase cloud thinning, which I'll talk a little bit about later, is one idea being proposed for the poles. Or if you have stratospheric aerosol injection, a lot of those tropospheric aerosols eventually will deposit towards the Arctic. So these are topics that are of interest right now. We don't know how effective they are. We don't know what the side effects might be. Of course, we need to engage with the people that live there, indigenous communities, and local governments. So anyways, I wanted to work on this topic, and so I contacted Ralph Kahn. He was at the time a research scientist at NASA Goddard Space Flight Center, and I wanted to do a NASA postdoc with him, and so we worked together to write a proposal looking at how biomass burning aerosols might affect clouds. And this is a picture from the 2008 ARCSIX campaign. You can see this big fire, and it's the smoke is kind of coming up into clouds, and you can see upwind of the plume and downwind of the plume, the clouds look different. That was kind of what I started out looking at in this NASA postdoc. And I just want to talk about the NASA postdoc, since some of you might be interested in that program. I didn't get it my first try. You can reapply, you can resubmit your application. So I didn't do anything, and I just got it on the next round. Right now it's really competitive, but it may not be that way in the future. We don't know. Right now it's hard. But it's a really great pipeline if you get it. To get a foot in the door, you get a lot of travel money, which is nice. It's 2 years, and then you get a third year if you're a supervisor or you have the funds. It's an award, quote unquote, not a salary. So what that means is that you don't get like Social Security and stuff like that. Just a way for them to like pay you less, basically. It's important if you want to do this to have like a NASA scientist mentor who can co-write your proposal with you. That will increase your odds of success a lot. And to target things that NASA cares about. So I can't speak on behalf of NASA, but my impression of having been a cooperative agreement scientist working with them for a while is that some things that could be successful are using their data. They love people using their data for aircraft, for satellites, missions. They want it to be in line with the federal administration priorities, and they want it to be in line with scientific community consensus on what's important. So those are all things to keep in mind as if you're developing an idea on that. So initially we looked at aircraft observations. We kind of wanted to start small and build up. So it's kind of the things we had the most confidence in. So we had confidence in aircraft data. We wanted to understand how they could help quantify aerosol and direct effects on liquid clouds. So here's a picture from the ARCSIX campaign of upwind. So here's a plume. It's blowing downwind here. These red lines are the back trajectories. And the blue lines is the aircraft. So it's sampled in the plume and also around the plume and back and forth across the plume. So this is upwind of the plume. You have these clean background clouds. And then in the plume, you have a lot of really smoky clouds. And then also we looked at just different data from lots of different campaigns, like ISDAC, ARCTES, and several other, Fire Race, others. And we collected all those data and looked at cases where there were smoky and non-smoky background clouds. And then we plotted them up to try to understand what relationships there were. This relationship is CCN versus cloud droplet number, but we looked at lots of relationships. And since we're looking at basically the same cloud, but just like in and out of this plume, we could get some information on they're basically comparable clouds for the most part. And so we can get some information on how smoke was affecting them. And so we found that in this like really intense smoke here, there wasn't enough moisture to actually nucleate a lot of the droplets. So actually the radiative effects weren't quite as big as, for example, when you look across the Arctic in more dilute air. In those cases, actually they actually mattered more because there was enough moisture for the particles to nucleate. And so something like half of all of the particles we calculated from our just basic calculations here were nucleating, half of the CCN. Okay, so then we wanted to look at satellite data. So satellite data has the benefit of being available in lots of places and over long periods of time. And if you use active data like from LiDAR and radar, you can see during polar night as well. And so that's great. But we wanted to start small and start with, could we see something in the easiest to understand clouds? So this ended up being like the 5% of clouds that were easiest to see. So the study is kind of an incremental step, but it was kind of a needed step before we move forward. So what we did is we used LiDAR data to detect aerosols, and we could only do that for thin clouds because otherwise the LiDAR data gets attenuated inside the cloud. And we did it at nighttime where the data are best and for predominantly liquid clouds. And then we looked at how those clouds changed. We compared clean clouds, all clouds, and polluted clouds. And we found that cloud optical depth decreased, cloud effective radius decreased, the number of clouds that were precipitating decreased, and the number of mixed phase clouds slightly decreased when there was combustion aerosols. So we saw these differences, but then, so we had some confidence that these aerosols were mattering in these clouds. But then the question is, how impactful is that? So what we did is we looked at all clouds now, not just these 5% of clouds. And this is a super basic calculation, but it was something to start with. We used the CloudSat FlexR LiDAR product to look at just what's the long wave cloud radiative effect at the bottom of the atmosphere for the lowest quartile of column black carbon versus the highest quartile. And here, just for reference, is where the sea ice was during that period. We found a really big difference, a 10 watts per meter squared difference in the surface long wave effect. So in principle, it could matter a lot, but there's a big caveat here, which is we also know that aerosols covary with meteorology, and so how much of this effect is from meteorology versus aerosols, and that's kind of a perennial problem with understanding aerosol cloud data, but at least we have some feeling that, okay, it could matter. So just to kind of illustrate that point more, this is a figure, this is kind of, I made this figure, but it's related to the study from Duda et al., where they discussed this warm air mass intrusion event during Mosaic. So they had a ship located here, and on one day they had this huge moist, warm, cloudy air mass passing through, and it was associated with polluted air also blowing from the continent here. And then if you contrast that to, like, for example, here it's drier, it's colder and cleaner. Like off the top, if you just, without careful understanding of the data, you might say, oh well, polluted equals cloudy, but you can't do that. The clouds are impacted by moisture and temperature as well, so you have to control for that when you're trying to understand these effects. So the way that we've been doing that with me and my colleagues is by using stratification, so basically breaking the data up into comparable meteorological conditions. So for example, here's relative humidity on this axis, here's temperature. The colors indicate how cloud fraction is changing. And this is for all cases of clouds, minus the part of the fraction of the subset of clouds that have low pollution, basically. And apart from the edges where there aren't a whole lot of data, you can see that once you control for meteorology, you see consistent decrease in cloud fraction when there's pollution. And so that's here. Like what we can do is we can average all that weighted by how common each of these meteorological conditions are, and get kind of an average for the Arctic. So across the Arctic, for those clouds, cloud fraction was smaller when there was combustion. The clouds were more likely to be in the ice phase, and they were slightly more likely to be precipitating. Okay, so let me take a step back. I'm going to continue with that in a second, but I want to keep kind of telling you like life lessons learned. So at that point, I transitioned from a postdoc to my current job, research scientist track. And I just want to talk quickly about the 3 tracks at Goddard, for those of you who might be considering a career in a place like that. So there's civil servant, those are people who are employed by the federal government. And at Goddard, that's about 20% of the workforce. And then there's cooperative agreement scientists like myself. I work with the university, I lead my own research, I write proposals. If I don't get grants, I don't get paid. Civil servants have that more like stable setting, I guess. But they can only apply to grants at NASA. Like I can apply to grants everywhere. And then there's contractors who get paid by civil servants to work on topics. And then they don't typically direct their own research. Some of them do, but it's like less common. Okay, so my experience transitioning from postdoc to research scientist track, I needed help. It was really helpful to have a really supportive mentor. So my second year, I wrote a proposal, didn't get funded. My third year, I wrote a proposal, didn't get funded. I did get one as a co-I, but in the meantime, like Ralph, who had been my postdoc advisor, supported me half the year, and then he paid for my third year of postdoc, and then finally I was able to bring in my own grants, and I have been, knock on wood, been able to do that ever since. But without his help, I mean, I don't know, I would have probably changed jobs. So it was really helpful to have somebody kind of in your court helping you. some tips for successful grant writing now that I've been doing this a while at NASA that might be helpful for you guys. It's good to attend trainings on how to write good proposals. That helped me a lot. People always underestimate how long it takes to write a proposal, especially for their first one. So take way more time than you think you're going to need. And then volunteer to be on review panels. That's really helpful. Typically, program managers like people to do that, and then you're just going to learn so much about what a good proposal looks like that way. And seek feedback from your colleagues, like, well before it's due, and that really can improve your proposal too. So some early career researcher lessons learned. Two-body problem remained a problem. When we moved back to the United States, my husband didn't find a job for like a year. He was looking, if you're constrained to one location, that's tricky. Luckily, he was able to work part-time from his job in Germany, and he was on parental leave for a while, and then he got like kind of a part-time job at University of Maryland, and then finally he got something. But it's tricky. I don't know what to say. Just something to plan for in your life, I guess. Transitioning fields can lose you productivity. I did it a couple times, and but I think it is a surmountable thing. Don't be afraid to do it. If you might need to be flexible at this time. Things are kind of unusual now, and you might find yourself in a position where you have to be flexible. It's going to be okay if you do. Your career will continue on. Sometimes if you really want something, like I really wanted to live in DC, we had to take a hit, a professional and financial hit to make that happen. To be in a position for that to happen, you have to actually have some money saved. So don't spend your freedom. Your money is your freedom. I know people don't, it's not good to talk about money, I guess, but I think it's important for students to know, if you save money, that's freedom in your career to take risks. And so it's just something to consider, it's something I learned anyways. I'm not saying you have to be super wealthy, but if you can save, it can be helpful for you to save to the extent that you can. And you can tackle hard problems. Aerosol-cloud interactions are the biggest uncertainty for a reason. They're challenging, and the Arctic is a challenging region. And it is possible to, your progress may not be quick, but it is possible to move that field forward, even if it looks hard. Okay, so then now I was starting to work on stuff that I got funded for. So one of the questions we had is, how does dust affect the prevalence of deep convective clouds? And I was continuing on in this question of how can we really be sure that the effects of aerosols on clouds are what we think they are? And so we're kind of developing the method over the years. And what we did new in this paper is that, so we saw these differences before when we controlled for meteorology, but now what we're doing is we're making sure that what's causing the signal really is what we think is causing the signal. So what we did is we look within meteorological bins, and we look at the factors that actually predict those differences within those bins. It was kind of a new step. And in this case, we started out thinking dust was going to be important for these deep convective clouds, and we saw that when we controlled for meteorology, dust did change it was associated with changes in the clouds. But when we looked at the factors that were actually driving those changes, it actually wasn't dust. It was marine particles. We think they were marine new particles that were actually coagulating onto the dust, and then when the dust is larger and heavier, and it would fall out, and then those new particles that would have been CCN no longer were in the system. So we were able to kind of get a better understanding of what's going on underneath the surface and have more confidence that what we're seeing is what we think we're seeing. So now we wanted to apply it to the Arctic again, but we needed to know a little bit more about what each of these aerosols, or could we actually identify aerosols well with reanalysis data? Because it's hard to observe aerosols when there's a lot of clouds like there are in the Arctic. So we just had to kind of validate that. I don't want to spend too much time on that, but long story short, there's a lot of uncertainties in aerosols from reanalysis products, particularly near the surface, because a lot of them don't include local dust. But at least we were able to do it with some confidence at around 3 kilometers. So I'll skip this in the interest of time. My postdoc's actually working on that. She's working on adding high latitude dust into GEOS, and then eventually it will hopefully make it into the MERA 3, the next version of MERA, the reanalysis product. So then we applied just looking at 3 kilometers where we felt comfortable saying we can actually get, compared to Calypso, we know that these reanalysis products work well. Then we looked again, same method, we looked at, we bin the data, in this case humidity and temperature, and we looked at the difference between clouds where all clouds in the subset that didn't have any dust, basically. And so we're looking for what are the signals of dust in the system. And so blue here means that it's icier when there's dust. and red means less icy. And when it's an empty circle, that means no change. And so it was kind of nice to see. Lab studies suggest that dust starts nucleating clouds around -15, and we did see around -15 that the clouds were more glaciated. But in fact, we actually saw a little bit before then, around -10, the clouds became more glaciated. So that could be because in situ things are different than in the lab. It could be that the IMPs in the Arctic are slightly more effective than they are elsewhere. Unclear still. And then we were interested in, so what does this matter in terms of cloud radiative effects? We weren't fully able to answer that question, but we were able to say that these effects were associated, at least, with cooling of the surface. That doesn't mean that they're causing that cooling. So we need to do more work to really fully flesh out that link. But we saw cooling with the surface associated with the dust after we did all this controlling for meteorology. So now I want to talk a little bit about ARCSIX. This is a project 8 years in the making on my end. We started from the beginning and wrote proposals and tried to get it funded, and was on the white paper. Paquita was part of this effort and wrote proposals. I think you were on the white paper, right? Yeah. So ARCSIX was an aircraft campaign from NASA. Michael was there too, and Andrew was also there. We were based out of Patuxent, Greenland. We had 3 aircraft. And our goals were to better understand the surface radiation budget, which is the energy interacting with the ice in the atmosphere. And specifically, we wanted to quantify how the surface and the clouds and the aerosols and precipitation all affect that budget, and summer sea ice melts. And we also wanted to improve remote sensing and models of the Arctic. So again, I mentioned 3 aircraft. It was a big program. We had like 150 participants, so it cost over $30 million. We were there last summer, or May, June 2024, and July, August 2024. So we had 159 flight hours, which makes this one of the longest aircraft campaigns ever in the Arctic. And in fact, it was the most comprehensive combination of instruments for this purpose ever out there, so in terms of clouds, aerosols, meteorology, sea ice, and remote sensing all at the same time. Oh, and there's a picture. I included this because there's Michael and Paquita. So my team we provided the forecasting and satellite analysis for this to optimize the flight planning across northern Greenland. So we identified satellites daily, data from the ground, from LiDAR, and from the AirNet sites. And we created maps from geos to try to estimate where these aerosols, this is mostly biomass burning. We had a lot of biomass burning during that time. And work with colleagues that can provide back trajectory information. And then we also used historical satellite data to help us better understand interesting places to go and just the context for the results. And that's still stuff we're still working on. But I showed you these data before. So now we know dust. We already knew dust was important, but now we know a little bit more about which conditions that it's important in. We unfortunately weren't able to sample too much dust, but we got some. We also established international partnerships to try to maximize the synergies between what we were doing and what other countries who were doing research in the Arctic were also doing. Lots of people are interested in the Arctic, so we worked with the Swedish Odin research vessel. We overflew them a couple times. We overflew long-term ground stations. We did one of the very first EarthCare underflights. EarthCare is another satellite from European Space Agency. I'm part of a 50-member aerosol working group. Paquita's part of the cloud working group, so lots of working groups working together to answer some of the targeted questions. We coordinated with some of these other ships that were there and actually put instruments on them to sample all at the same time as us. So that was a lot of work, but it was worth it because we got all this extra information as context for our project. So it's still early to show too many results. These are some. This is from Armin Narir from June 10th. We overflew Eureka, and they saw a local dust event. Unfortunately, we didn't sample it with the aircraft that had the chemical composition, but they saw a local dust event that was 2 kilometers high in the atmosphere. So that's never been observed before, such a major dust emission event. We saw tons of aged Canadian smoke. We actually sampled what we believe to have been, so there's a volcano that erupted in Iceland, and then it moved up and across northern Greenland, so we got an aged volcano plume, which is, I think, the first time that's ever been observed in such careful detail. We're still working. The paper isn't done yet, but it's something we're working on. We got marine aerosols and studied those. We flew as low as 60 meters above the sea ice, so that was pretty cool. Okay, so I'm going to change gears again, doing lots of things. So I'm also involved in this international group called QuiESCENT. We study the indirect effect over the Arctic. We recently had a meeting. A bunch of participants from around the world came together and kind of brainstormed on aerosol-cloud interaction science and where we could go from here, and in particular in context of the International Polar Year that's coming up in 2032. And so that's an effort where countries around the world get together, put money, and do research at the same time, coordinating with each other. And so this would be the 5th International Polar Year. The last one was in 2008, I think. And usually Congress appropriates money for that. But of course the US Decadal Survey is coming up. That's another opportunity for those who don't know to you can write in white papers for that and say, here's what the community thinks is important for science going forward. So this was meant as kind of a basis for that too, and also for individuals to reference for if they're doing Arctic aerosol cloud interaction research. So we wrote a paper based on that workshop, and I just want to talk about some of the findings from it. So as a community, we kind of decided, or we kind of talked about some of the research challenges and priorities in this field. So secondary ice production is a big uncertainty. It has been for a long time, and remains that way. Getting continuous long-term observations of cloud-active particles remains a challenge too. Vertical profiling is a challenge, especially right now. People are starting to try to get ice nucleating particle and CCN information from LIDAR, and there isn't much validation data for that. Getting enhanced real-time chemical composition, similar to what Cassie's group is doing, single particle analysis and so forth, that would be really helpful. Atmospheric dynamics, driving turbulence and entrainment, deposition, these are really hard for models to parameterize, but they really matter for our ability to predict clouds in this area and how it's changing in the future. We don't currently integrate the lab and field group communities very well, like cloud chamber groups. Those are something that as a community we can do better. Satellite resolution remains a challenge to observe things like leads, which can be quite small, but they can still be important when they're small, or aerosol dust events from point sources, which they don't typically get. That event where there's a 2 kilometer high dust event is not typical. Usually it's much smaller point sources from a large area, and that's harder to observe. And then, again, I talked about this before, but how the changing Arctic and the meteorology there affects cloud radiative effects is a big uncertainty. But there's been some technological advances that people were interested in working on this type of work that might be helpful. So of course there's machine learning. We can better use all the satellite data we have, or all the long-term observations that exist. More regular vertical profiling with uncrewed aerial systems, or tethered balloons, or miniaturized instruments. That all could be great and helpful. That could also help us increase our spatial sampling and get extra field sites for context during field deployments with aircraft, for example. Now we have this new EarthCare satellite. We get Doppler radar data and other information that can be helpful. We also having better ability to interpret the satellite data, both through machine learning and also through some of the methods I talked about. And we can now track the temporal evolution of clouds because a lot of the satellites are polar orbiting, and so you can kind of watch them in a quasi-geostationary way. And like I mentioned, the LIDAR estimates of the cloud nuclear particles is something that's an interesting thing that might be worth looking into in the future. Okay, and last thing, I'm switching gears one last time. So I'm also involved in some climate intervention science. So I mentioned this idea, mixed phase cloud thinning. It's this concept. It's not well understood right now. There's only been really one paper, the Villanueva et al. Paper, which was a modeling study on it. But this cartoon kind of illustrates the idea. So during nighttime over the poles, clouds sort of act like a blanket, and they trap heat near the surface that gets emitted. But if those clouds were to thin, for example, if ice nucleating particles were to be added and those cause the clouds to precipitate more, or if they just thin optically, so the liquid changes to ice by adding these ice nucleating particles, then more heat can escape to space through those clouds. And so the idea is, if you were to add ice nucleating particles, maybe you could make the surface cooler, and then maybe that way you could preserve some sea ice. So this is very far from actually being implemented. It's more at the stage of, is this even worth studying, or could this even work at all? So we're trying to, so this project's being led by my colleague Jasper Koch at UCLA, and he's currently looking for his postdoc, if people are looking for postdoc. yeah, so we're using satellite data to try to better understand if this could even work in the first place. So what we're doing is, instead of some of the work I showed before was comparing when there were aerosols versus when there wasn't aerosols. Now what we're doing instead is comparing the Arctic Ocean to the Southern Ocean, because the Arctic Ocean actually has a lot more ice nucleating particles. It's closer to land than the Southern Ocean. So it's sort of a natural experiment where we can compare one location to another. They're both cold, and see if we see differences in the clouds. But of course, they're not exactly the same systems. It turns out that we looked for comparable meteorology, basically, and we only want to compare when we can do a fair comparison. And about only half of the time is there actually comparable data, because the Southern Ocean is windier and so forth and so on. So, but when we've been finally by the data and we compare the Southern Ocean to the Arctic Ocean in the same meteorology, that's what we were interested in looking at. And again, using satellite data to do this and reanalysis products. So this is all preliminary. We're still working on this, but this again is a plot of the various factors that could be explaining those differences after we've been. And we want all these meteorological factors here to be low, because if they're high, that means we haven't adequately controlled for meteorology. So using a generalized additive model, the percent deviance is generally below 6%. So that means we do a pretty good job of being sure that meteorology isn't causing any differences between the two systems once we're comparing in similar meteorology. So then we look at the data for open ocean and sea ice separately. So it turns out that there are cloud radiative effect differences after we control for meteorology in comparable bands. So that's in line with this concept of mixed phase cloud thinning, except for over open ocean where there wasn't much difference for the bottom of the atmosphere. But for the top of the atmosphere, there were differences. But you can see that the effects over sea ice were different than the effect over open ocean for the top of the atmosphere. So that means, like, if this is correct, and this is still preliminary, but if it were correct, then you may not want to deploy over the open ocean, but maybe over sea ice it could work. Potentially. This is like still early, so preliminary. We also looked at other, I don't know if you can see that, sorry, the font's pretty small, but we also looked at cloud properties and looking at how those change between the two systems. So over sea ice, we found not any big changes in cloud fraction, but there was glaciation of the clouds, as you'd expect. And there was also an increase in cloud optical depth. So those are both they're optically thicker in the Southern Ocean. So that's in line with what you'd expect. Over open ocean, it was icier, as you'd expect, and the clouds were more frequent over the Southern Ocean, which you'd expect, but the clouds were optically thinner in the Southern Ocean, which is not what you'd expect. So we're still trying to analyze what's going on here and try to understand what this all means. Okay, so now I'm done with the science. I'm going to end on a couple science tips I got that were told to me that I found particularly helpful. Some of these, so I got the opportunity to go to a Nobel laureate meeting, and so these are actually from Nobel laureates, and they've been useful for my career, so maybe they'll be helpful for you too. So plan experiments carefully. So what they told me and the other people there was that your brain can often trick you. Subconsciously it can cause you to reject or fail to investigate evidence that's kind of contradictory to your hypothesis. So they were really strongly recommending blind testing and calibration. So what that means is you develop a method that you're really confident in, and you're willing to accept whatever the results are, independent of whether it fits your hypothesis, and then you do it, but don't look at the results until it's like done. So that's one way you can do it. I try to do it that way, but sometimes when you get confusing results, you have to go back and make sure. But anyways, it's a method that has worked for me for the most part, so you could try it if you don't already do it. Another interesting tidbit they gave me is that a hypothesis isn't always necessary, and I'm going to take a step back and say for a proposal, a hypothesis really may be necessary because reviewers don't like it when you don't have a hypothesis, but for your own science, it can often be more important to present a problem rather than a hypothesis. So one of them, I put in quotes, they said, once a fundamental question becomes a well-formulated scientific question, it can be answered. So there's nothing wrong with guessing at a hypothesis and following up on it later, but it's just something to consider. I found it helpful for me. And then this one's not from a Nobel laureate, it's from a program manager, but those are the ones who decide who gets funding, and I thought it was really an interesting perspective. And I won't say from what agency they were, but they said that not all advances have to be big. Science is kind of like a pyramid, at least this was their own personal perspective. All of the little stuff is at the bottom, and that's the vast majority of all our work, and that doesn't mean it's not important. Maybe 1 or 2 papers make it to Science or Nature or whatever, but they're all building on all that bottom stuff. All the little stuff matters too, and so just keep that in mind. Like, don't feel like a failure if not all your papers are in Science or Nature or whatever. It's all important. Interactions with other scientists are critical. I talked about that in my own experience, but this is something that the Nobel laureate said too. Both collaborators and competitors improve your science. And then they talked about tips from their perspectives on promoting successful collaborations. So they said, learn at least one thing deeply. So people will come find you and talk to you and want to collaborate with you, that you have something to offer. Build long-term trusted networks throughout your career. They recommended maintaining a professional distance with those working for you and being proactive recruiting good people. And they also recommend working in person with your collaborators as much as possible. So one scientist recommended, for example, formal meetings at least twice a year when you have projects. And likewise, video calls are better than phone calls. And then lastly, be flexible in the face of rapid changes in technology. Scientific skills will transcend over your career. Technology changes, like in my career, AI came to be a thing, and I'm sure there'll be more things coming in the future during your careers. Scientific skills, like the base scientific skills, will transcend any of these technological changes. Yeah, so I think that's it. I just wanted to acknowledge all the people who've helped me. I only started writing this. There's many more people, but some of the people that contributed to this were, of course, Dennis Hansell and Joe Prospero, Lillian Custals, Miguel Isaguirre, Mike Trapp, Charlie Farmer, and Wenhao Zhao. Of course, my postdoc advisors, Andreas Oschley, Zinab Khan, and my current postdoc, Catherine Moore, and funding from lots of different sources, NASA and the German Sopran and Simons Foundation and EGU and IASC, so lots of funding. And anyways, and thank you all for hosting me and listening to me rant at you for an hour. I hope at least some of it was helpful.
Thanks for this curated talk to the Rosenstiel audience. We have time for, I think, like 2 questions. That's a question, right?
Yeah.
Not a comment. Okay.
Yeah, do you look at dust and ice? Yeah, do you look at dust and trapped in glacial ice to get a time history of before we had scientific sampling equipment and the like?
I don't personally, but people have done that. Those data sets do exist, yeah. On the Greenland ice sheet, for example.
Okay, thank you.
And there have been big changes. My understanding is there have been big changes over time in the amount of dust that was there or not there.
So Lauren, my question for you is, what advice would you give our grad students who are thinking about an international postdoc? What sort of tips and tricks would you give them to build those collaborations, to get those opportunities?
I guess I'd say never too late to start building those networks. So if for example, I did like the 3-month stint, and then later that led to a job with that same person. You could try to start forming collaborations now as a grad student to kind of get to know people and have them get to know you. It's been a while, so I don't know what the current status of everything is, but that helped me anyways.
I don't know if we list international visitation opportunities. I don't actually know of those very much.
Yeah,
How
at the
did you
time,
find
I
this?
actively reached out to him, and then it turned out he was internally was able to procure funding to host me. I think I already had Dennis's grant that probably could have paid for it, but then he was able to get internal funding. So you might not see opportunities listed, but you might be able to contact someone you want to work with, and then they might have opportunities available to them that you might not be aware
Okay.
So just a quick follow-up on that, just for some of the students in the audience, like Max Planck does that, so they hosted Anne for a month to do measurement, and this just came from me chatting with someone at Max Planck and chatting about our science, and then they do have funds available to host students, so that's a good way to build an international network.
Yeah, and attend workshops and talk to people. That's the other thing. Like if Erasmus is looking for a way to kind of spur that, they could like help support students to go to workshops so that they can make those connections. I think they had always been doing that. Maybe you guys still already do that, but when I was a student, that was really helpful for me.
Yeah, we should look into that. I don't know if we have that anymore.
I think so.
Any other? I kind of have a science question, and you can say no. A lot of people use Mera 2 to pull out the aerosol part from the meteorology part. And now I guess we're moving to Mera 3. What do you think the strengths are, or maybe the big leaps that are happening to Mera 3, and where do you see the biggest problems with Mera 2?
Okay.
And if you may not know. So
I do know in great detail in my email, but at the top of my head, I can forward you an email I got from Pico Arco on exactly that topic. So after Mera 2, there's actually going to be Mera 21C, which is coming out very soon, I think. So that's kind of an intermediate step. And then later is going to be Mera 3. So we won't have, Catherine's work on high latitude dust won't be ready in time to incorporate into Mera 21C, but it will be hopefully ready by the time Mera 3 rolls around. So some of the, as I recall off the top of my head, I think some of the advances are lots of code has been improved to incorporate different processes. I think it's going to be higher resolution. I could forward you the email. I don't remember off the top of my head, but I do have an email about all those changes.
Yeah. All right. Thanks for coming. And Laurel is going to be at the wet lab later. If you have further questions, or you can ask her now.